Good morning everyone. Today we're going to discuss our topic. Our topic for today's video is truth values of propositions and forms of conditional propositions. At the end of the video lesson expected to learn, determine the truth values of propositions. Illustrate the different forms of conditional propositions. Truth table is a mathematical table used to determine if compound statement is true or false. In a truth table, each statement is typically represented by a letter P, Q or R, and each statement also has its own corresponding column in the truth table that lists all the possible truth values. For example, let's take the statement, "It is a sunny day." So our P is "It is sunny day." Negation. The negation of a statement, called not P, is the statement that contradicts P and has opposite truth values. If our P "It is a sunny day" lets us find its negation, that will be not P, or "It is not a sunny day." Below is how both of these possibilities are represented in truth table, in which T represents true and F represents false. So there's two columns in negation. This is for P, and this is for not P. So if your P is true, then not P is false. If your P is false, then not P is true. Conjunction. A conjunction is a compound statement representing the word and. For example, we have the following statements. P, "It is a sunny day." Q, "The street dance will continue." The conjunction P and QPQ is, "It is a sunny day," and "the street dance will continue." So let's go to the truth table for conjunction. Here is the truth value showing the possibilities of a conjunction. So there are three columns in conjunction. The first column is for P, the next is for Q, and P and Q. So in the first row, P can be true and Q can be true also. Always remember, in conjunction, it is only true when both components are true. So in this case, both components are true. Therefore P and Q will be true. Next we have true-false. Since the other one is false, that will be false. Also the first part is false, then it is false. And since there is no true at all, that is false. Always remember, in conjunction both components must be true to make conjunction true. Next is disjunction. A disjunction is a compound statement representing the word or. In order for the disjunction to be true, one or both of the original statements has to be true. P, "It is a sunny day." Q, "The street dance will continue." The disjunction P or QPVQ is, "It is a sunny day," or "The street dance will continue." So this is truth table for disjunction. And there is a three columns again, for PQ and P and Q. So since it's both true, then that will be true. The next one, there's one true. So therefore that's true. We can see also other true for Q. That is true. There's no true at all, and that is false. So in disjunction, at least one of the component is true, then the disjunction will be true. Otherwise, if there's no true, it will be false. Next is implication. An implication is a conditional if-then statement that is being divided into two. The for-up part or the if part is the antecedent, or called as the hypothesis, and the second or the then part is the consequent, or called as the conclusion. P angle ABC is a right angle 90 degrees. Q angle ABC measures 90 degrees. The implication P greater than Q is, if ABC is right angle, it measures 90. Truth table for implications. Here is the truth value showing the possibilities of an implication. The first columns is for P for Q and for P then Q. In implication, all the possibilities will be true, except that when the hypothesis is true and the conclusion is false, then P then Q will be false. So again, all of this will be true except that when hypothesis is true and the conclusion is false. Biconditional. The biconditional of proposition or statement P and Q is denoted by P less than greater than Q, P if and only if Q. P angle ABC is right angle. Q angle ABC measures 90 degrees. The biconditional P greater than Q is, angle ABC is right angle if and only if it measures 90 degrees. truth table for biconditional. Here is the truth value showing the possibilities of biconditional. So this the first column for P, column for Q, and column for P if and only if Q. So in biconditional both components have the same value. Then it is true, otherwise it's false. So in this first case, they have the same value, so that is true. So in the second one they don't have the same value, so it is false. And the third is false also. And in the last case they have the same value, so they become true. So remember, in biconditional, if when they have the same value it will become true. Logical equivalent. The two proposition P and Q are logically equivalent, denoted by P if and only if. Logical equivalence can also be expressed in terms of a biconditional statement. Two propositions P and Q are logically equivalent if the propositions P if and only if Q is always true or is a tautology. Example: show that P then Q is logical equivalent to not P or Q. We shall call this logical equivalence or the switcheroo law. Okay, so this is the example. We're going to show that P then Q is logical equivalent to not P or Q. So we're going to construct a two-column table for P and Q to write all the possibilities. Okay, so we will add another column for P then Q because of this. And then we're going to follow the implication. So remember that in implication this will become false if the hypothesis is true and the conclusion is false. So in this case we will write here true and then false for in this case. And then let's add another column for not P. Okay, let's add another column for that. And then for not P we will just look at the values of P. So given the value we're going to negate because of the symbol for negation. So from true that will become false, and then from false that will become true. So let's add another column for not P or Q. So since it involves disjunction we will follow that. And we are going to give focus on not P and Q. And then we will follow the disjunction in this junction at least one true. Then the disjunction will become true or one or both of them are true. And the disjunction will become true. So in this case, on the second case, as you can see, both of the components are false, so therefore it is false. Next, for the first and third and fourth, they are all true. So next, as you can see, so P then Q and the values for not P and Q are the same. So we can say that P then Q is logical equivalent to not P for Q. Different forms of conditional proposition. Suppose P and Q are propositions. From the conditional proposition P then Q, we can derive three other conditional statements. What are those? Converse Q then P. Inverse not P then not Q. Contrapositive not Q then not P. So this is the given. P then Q. If Matilda is in grade 11, then she is a senior high school student. So let's find the converse or the Q then P. If Matilda is a senior high school student, then she is in grade 11. The inverse or not P then not Q. If Matilda is not in grade 11, then she is not a senior high school student. The contrapositive or not Q then not P. If Matilda is not a senior high school student, then she is not in grade 11. So okay, let's try again. So this is the given. Let P then Q. If 3x plus 5 equals 26, then x equals 7. The converse or P then Q. If x equals 7, then 3 by plus 5 equals 26. The inverse or not P then not Q. If 3x plus 25 is not equal to 26, then x is not equal to 7. The contrapositive or not Q then not P. If x is not equal to 7, then 3 by 5 is not equal to 26. So that's all for today. We hope you enjoy learning about our topic. Thank you for watching.